Skyscrapers, the titans of city architecture for more than 100 years. From New York's Empire State Building to the incredible Petronas Towers in Kuala Lumpur, skyscrapers dominate urban landscapes across the world. There seems to be no limit to our appetite for super tall buildings and no boundary to the aspirations of the people who create them. Within such high and crowded structures, the consequences when things go wrong can be catastrophic. But from such terrible events comes knowledge. And with knowledge, the opportunity to improve, shape, refine. Today, every major skyscraper under construction across the world is literally built from disaster. Skyscrapers define the modern age of construction, transforming our cities and the way we live. No other design so readily accommodates the voracious need for space in our urban centres. But there can be a high price for this particular solution to overcrowded city life. Mexico, 1985. The Pino Suarez Towers collapsed in an earthquake. In London in 1968, part of Ronan Point tower block came crashing down. In 2005, the Torre Windsor skyscraper in Madrid was devastated by fire. One of the very newest skyscrapers under construction is the Federation Tower in the heart of Moscow. Its designers believe that when finished, it'll be the strongest and safest super skyscraper ever built. The chief engineer of this Russian revolution is American Brad Marmsden.
This super high-rise structural steel building hasn't been part of Russia's construction history. I mean, some things just couldn't be done here when we started the project.
Upon completion, the Federation Tower will be the tallest building in Europe at a dizzying 365 meters.
For Russia, at least, it's a unique. It's height, it's technology. We try to do something that was never done before.
With no history of skyscrapers in Russia, the Fed's backers have brought in expertise from around the world, employing construction experts from 20 different countries.
As you see on this project, we've got Chinese contractor, China State. When I built this project, Tower West, we had Turkish contractor. Different cultures, different mentalities. When I came to Moscow, I spent the first year as like a professor of construction. In the Middle East, this is old news. Here, this is leading-edge technology.
They're working 24/7 here at level 56 to complete in record time for 2010. Each story is going up in just 5 days. Russia's dream skyscraper is intended to set a new world standard in strength and safety, avoiding the pitfalls of the past. Early one morning in East London in May 1968, a small gas explosion high up in a tower block was to have huge consequences.
I started walking down Bridgeland Road, and as I stepped off the pavement, the ground shook. But almost instantaneously, there was a loud boom overhead that made me duck.
People have been coming in their thousands to stand in the streets nearby and stare upwards disbelievingly at this great wounded slab of concrete and glass.
What caused people to gaze in disbelief was the astonishing disintegration of one of Britain's most popular housing developments, fallen victim to sudden and profound structural collapse.
A sight like that you'll never ever forget. I don't think you could ever forget anything like that. it's that clear in my mind because it was such a shocking sight. You don't expect a structure of that magnitude to fall the way it did.
The reasons behind the collapse of this London tower block were equally shocking. When Ronan Point collapsed in East London in May 1968, both the authorities and the public were mystified. Ronan Point had been built to a radical construction design known as the large panel system, introduced from Scandinavia, where precast concrete panels were used for multi-storey homes. Initially designed for buildings of 5 stories or less, in Britain the system was for the first time employed to erect taller buildings. A comparatively minor incident had sparked the chain of events that blew the name Ronan Point into the architectural history books.
One of the occupants lit the gas stove in her flat to make a cup of tea. There had been a leak in the gas system overnight, and it ignited the gas in the room and caused a big local explosion inside her flat.
This local explosion blew a panel clean out of the tower, but the damage did not stop there.
There was like a very loud crackling noise, and then sections started to fall in on top of themselves. Outer sections was folding down and just ripping off. Others was falling down onto floors below. The weight of it was giving way and that was flopping down. It just felt like a house of cards.
What Ray Hollins was witnessing was a phenomenon described by architects as progressive collapse. Progressive collapse happens when the failure of a small part of a structure leads to the whole building tumbling down on itself. In this case, the gas explosion blew out just one prefabricated wall panel, but it led to the entire destruction of the tower's southeast corner. This progressive collapse at Ronan Point killed 4 people and injured more than 17 of the 260 residents. Immediately afterwards, investigators began to search for the causes of the disaster.
Why should this happen in 1968, in the middle of the 20th century, when we knew we had well over 100 years' experience of building?
Investigators needed to find out how a relatively small internal explosion could cause such sudden and total progressive collapse of the entire corner of this multi-storey building.
There must be something wrong with the construction. Something has been left out. It's either been left out in the design, in the construction, or in the workmanship, putting it all together.
It turned out to be all 3. Investigating engineers found that the structure of Ronan Point relied mainly on gravity, downward pressure, to hold everything together. A force or load going upwards or sideways, as happened when the gas ignited, had simply not been considered. Investigators also found that poor construction in the joints meant the blowout resistance of the whole wall panels was less than that of an ordinary pane of glass in a window.
This here is the dry pack, which is supposed to transmit the load from the panel above to the panel below. This should have gone over the full width of the joint, but as you see here, at best it is only over the inner half.
How many joints have you found in this state?
All of the joints have been in this state. And one of the surprising things is that not a single joint that we've so far exposed has been properly constructed.
The failures exposed at Ronan Point caused a public outcry and led to the introduction of new and much more rigorous building standards.
It changed the rules and regulations that we had to work to, and it still is a big influence today, 40 years on from when it first happened.
The new codes required all new buildings to be able to resist an explosive force of at least 5 pounds per square inch. Tests showed Ronan Point could only resist a blast of 1.8 pounds. As an alternative method of design, any key element of the structure had to be capable of being removed without causing collapse. This was to be achieved by providing alternative load paths.
Engineers wanted to make sure they didn't collapse, and in particular that a relatively small accident affecting just a small part of a building didn't act as the trigger to a complete collapse.
Across Britain, many tower blocks built using the large panel system were demolished, and no new ones were ever built using this method again. New skyscrapers were being built, but now they incorporated the lessons of Ronan Point. The first major skyscraper to be built in London after the Ronan Point disaster was Tower 42, completed in 1980. At 183 metres high, it would remain Britain's tallest skyscraper for 10 years.
Tower 42 is an in situ reinforced concrete building. The structure is monolithic. It's like a tree. It's very, very strong.
To give alternative load paths, Tower 42's engineers designed strong and continuous connections, linked by a robust central core. The tower is specifically designed to resist progressive collapse.
The connections here between the beams and the columns have continuity. That means that you can transfer load through them vertically or horizontally. The beams don't just rest on the columns, they are joined up together so that you can transfer load through them. So that if something happens, if an unusual load or a very large load occurs, this building doesn't come apart at the joints.
In 1993, this resistance was well and truly put to the test. A large bomb exploded in London's financial heartland and wreaked havoc, destroying a number of buildings and causing more than £1 billion worth of damage. But amidst the chaos and debris, Tower 42 stood tall. This skyscraper's design to resist progressive collapse saved it from disaster.
This building really didn't get damaged at all by a quite serious bomb blast quite close to it.
20 years after Tower 42, more lessons from Ronan Point were applied in the engineering of London's iconic Swiss Re building, affectionately known as the Gherkin. Here, engineers addressed the issue of alternative load paths by introducing a unique steel structure around the outside of the building, called a diagrid.
The main feature of the structure is this diagonal arrangement of columns around the perimeter, which we call the diagrid. And the structural design is essentially to create a symmetrical, triangulated framework of steel elements, which creates a balanced and robust perimeter. That structure, as well as taking all the gravity, the weight of the building, it also provides the stability against wind loads.
The diagonal grid of the pattern on the structure on the outside face isn't just there to produce an interesting shape or for people to look at. It is the structure, a series of interlocking steel pieces that cross over, carry the load, and they form a tube around the outside of the building, and that is a really strong way to make a tall building stand up.
The Gherkin uses an engineering system called redundancy. This is the duplication of critical components to provide backup or fail-safe, ensuring the safety and reliability of the building as a whole. The Gherkin spreads the load outwards, shifting its weight away from any damage caused in the event of a disaster. Its engineers believe its structural ability to resist progressive collapse is second to none. That is, until this skyscraper is complete. Moscow's Federation Tower, due for completion in 2010, employs not just one alternative load-bearing system to prevent progressive collapse, it has three.
It's a kind of belt and braces approach, which gives what engineers call redundancy, alternative load paths for the load to be carried back to the ground.
The first load-bearing system is a central concrete core, similar to that used in Tower 42.
The way the building works is in the middle of the building, you've got the trapezoidal concrete core, which is sort of like a tree trunk that centralizes the whole building and holds the middle part of the building together and holds it up. The core stabilizes the tower from the center.
The second load-bearing system uses a perimeter frame, like the gherkin. But here it is made up of 26 concrete columns reinforced with steel bars, called rebar, on each story, linked by beams to resist side loading.
To make sure that we have vertical continuity in the columns is instead of splicing the bars with an overlap splice, we're actually threading the ends of the bars and screwing on mechanical couplers, creating a very tight, very solid tensile connection for the rebar. So it's almost like this rebar all the way down to the ground is a continuous steel tension rod running through the vertical column.
The vertical columns are securely connected to the concrete floor slabs at every level.
On top of that, we've got some really nicely tied up and closely spaced stirrups that are running across all the slab rebars. So what that does is it makes the joint between the slab and the column very strong and very stiff and very resilient.
And the Federation Tower has a third system to spread the load and thereby prevent progressive collapse. Positioned at 4 levels throughout the building are outriggers, a system of reinforced crisscross concrete beams which reach out from the central core to the perimeter, linking the whole structure together.
The outrigger is spanning out to the perimeter, and it runs into the belt truss here. So this truss, these diagonals are making up what's called the belt truss. They span all the way around the building, and the outrigger is spanning into this. It hits down on this, the load spreads out through diagonals and into all the columns, all the perimeter columns. So in the case of a catastrophic emergency, if one of these columns happened to be cut off or removed or something during the life of the building, the columns below could hang themselves up through the steel inside the column to this belt truss, and the load could span back through the belt truss either to more columns or even into the outrigger and into the core.
With these 3 systems in place, the Federation Tower promises to be one of the strongest and most stable skyscrapers the world has ever seen. And its strength doesn't just lie above ground, it's incorporated into its very foundations. The Federation Tower is anchored to the ground with 14,000 cubic meters of high-strength concrete, poured non-stop over 4 days to create a massive anchoring slab. What's more, the pouring took place in the midst of the harsh Moscow winter.
During the early months of this project, we were pouring in minus 38 degrees. That meant that we had to have cocoon situation to keep the concrete warm. The concrete pumps had to be cocooned, the concrete lines had to be traced, but inside the cocoon we were achieving plus 12.
The foundations have been piled down through 2 layers of rock, filling any voids with concrete.
They had a huge crew of people in here with concrete just coming around the clock pouring, and they keep it wet through additives in the concrete that help it set a little bit slower than normal concrete. They're vibrating it with vibrators all around to make sure the concrete flows freely throughout the whole course of the pour. And what that did was it allowed us to have a very nice, stiff and solid foundation mat to sit on top of all these piles.
Engineered to resist forces exerted from above, from the side and from below, and with its strength reinforced by foundations 20 meters deep, the Fed is a building capable of withstanding almost anything, even, its builders believe, an earthquake. Moscow is not in a seismic zone, but the designers of the Fed are taking no chances. Indeed, engineers have learned a great deal about the construction of skyscrapers from analysing the impact of earthquakes on tall buildings.
The effect of earthquakes on buildings, of course, is one of the few opportunities structural engineers have to test what they've designed virtually to destruction.
But it wasn't until the Mexico City earthquake in 1985 that a discovery was made which would revolutionize the design of our tallest buildings. Earthquakes are one of the greatest natural challenges for the architects and structural engineers who design tall buildings. But it's the lessons learnt from earthquake disaster that inform the design and building of skyscrapers all over the world, even in non-seismic areas. In September 1985, Mexico City was struck by a devastating earthquake. that measured a staggering 8.1 on the Richter scale.
Devastation in the heart of one of the most densely populated urban areas on Earth. 30 hours after the 5-minute quake, Mexican authorities...
At least 9,000 people were killed, and tens of thousands more were injured. Over 50,000 buildings were destroyed or seriously damaged. More has been learnt about building construction from this quake than any other.
The 1985 Mexico City earthquake led us to see that the earthquake really does seek out the weakest detail.
One important discovery was the way in which steel multi-story buildings perform in earthquakes. The steel-built 22-story, 3-tower Pino Suarez complex collapsed due to column failure. The columns had been made out of steel plates welded together to form a box shape. The earthquake had stressed the side welds of the columns beyond their strength. As a result, the welds were damaged, the steel columns buckled under the load, and the buildings collapsed. The way pieces of steel are connected is vital to maintain what engineers call ductility, or how far they can stretch before they fracture.
Ductility is a measure of how much an element can stretch beyond the point it actually reaches its maximum strength.
Steel constructions can be especially vulnerable at the point of a weld.
Weld metal is intrinsically less ductile than the parent steel material. And if the welded connection isn't a lot stronger than the member that it is connecting to, then it will tend to fail.
It's a lesson being taken to heart 7,000 miles away in Turkey's biggest city, Istanbul. This is a high seismic zone, and it's only recently that skyscraper development has been allowed here. Upon completion, the Diamond of Istanbul will be Turkey's tallest skyscraper, 270 meters high. Like the Federation Tower, the Diamond has a strong concrete central core. But joined to the core, there are 3 towers in the shape of a Y. And controversially, these towers are being built in steel.
This is going to be first steel construction high-rise building in Istanbul. And maybe it will be the highest one in Europe.
Turkish engineers are using a technique called full penetration welding to make sure their steel columns don't rip apart in an earthquake. The Diamond is using specially commissioned 12-meter lengths of Luxembourg steel for its columns. These are positioned one on top of the other, then skillfully joined together with a full penetration weld, as distinct from the side welds used in Mexico. With experts predicting a major earthquake in the next 30 years, there's no room for error.
Burada kolonların birbirlerine eklenmesini, yani bu kaynakları gördüğünüz gibi full penetrasyonlu dediğimiz tam nüfuzetli bir kaynakla eklenmesini görüyorsunuz. Bu şekilde bir bağlantıyla artık biz bu kolonu, alttaki ve üstteki kolonu monolitik bir eleman gibi, tek yekpare bir eleman gibi düşünebiliriz. Bu kaynakların kontrolleri röntgenlerle yapılmakta ve kaynakların kalitesi sağlanmaktadır.
Unusually, this building has got connections between the columns made with full strength, full penetration butt welds between the columns, done on the site. Now, that's pretty unusual, even today, to carry out full strength, full penetration butt welding on site. It's very often carried out in a workshop, in a factory situation where the conditions are easier to do the work, it's a controlled environment. It's less easy to do on a site, and it has been considered to be difficult in the past, but people are beginning to adopt site welding more, and the benefits that it brings is to provide complete continuity at the junctions in the columns so that they, in effect, run through as just one member right from the bottom to the top of the building.
Yatay yükleri taşıyacak olan, yani özellikle binanın dış kontüründeki bizim moment aktaran çerçeve.
The columns are then attached to beams using a specially designed bolt and plate system known as slip critical jointing.
Sadece düşey yukarı altına çalışan ana şeyi bütün dış çerçeve.
128 bolts, each one tightened to a tension of 35 tons, connect the beam to the column. The plates sandwiching the beam act like huge washers, providing friction and ensuring that the connection is stronger than the beam itself.
The main purpose of the slip critical connections is to reduce movement in working conditions. That is, there should be no movement because it's a frictional connection.
The key features of an earthquake-resistant building are attention to detail at the connections, making them ductile and able to absorb energy. And actually, it's the same requirement that prevents progressive collapse of buildings anyway. So the features that have been introduced into earthquake-resistant buildings are actually finding their way into tall buildings generally.
Both full penetration welding and slip critical jointing were born out of disasters resulting from previous earthquakes. Now, all across the world, buildings are using these methods. But there was another, more surprising lesson learnt from the Mexico City earthquake. It was discovered that when the earth shakes, very tall buildings often remain standing, while their lower level neighbours collapse. The 7th-floor Regis Hotel, one of the oldest low-rise multi-story buildings in Mexico, was totally destroyed in the 1985 quake.
In this block stood the Regis Hotel, where at 7:20 that morning, the first of 400 guests had been sitting down to breakfast. As both wings collapsed, all but a few perished.
And we also heard the Regis, the facade, the front started to fall off, and there was panic everywhere.
But while many comparable, smaller multi-story buildings fell down, some of the tallest buildings in Mexico City stayed up, undamaged. Torre Latino Americano at 182 meters, and the Pemex Tower, even taller at 211 meters, were both unscathed.
Contrary to what people might imagine, many of the tallest buildings survived completely intact, whereas some of the mid-height buildings and indeed some of the low-rise buildings fully collapsed. And this focused attention on something called the natural frequency of a building.
Natural frequency is the rate which a building vibrates in response to an earthquake. The Torre Latino Americano and Pemex Tower fared well because they were so tall that their rate of sway was much slower than that of the shaking ground, so they didn't resonate with the ground motions. Their natural frequency was outside the range of the seismic tremors. Engineers now believe that skyscrapers are actually safer in seismic zones than lower multi-story buildings. That's certainly what the designers of this skyscraper hope. At 225 meters high, the Torre Mayor in Mexico City is Latin America's tallest building. Completed in 2003, it's designed to withstand a mammoth 8.5 earthquake on the Richter scale. Its engineers have enhanced the effect of its natural frequency with technology developed from the US military, dampers. These are like giant car shock absorbers.
The main purpose of a damper is to absorb energy, absorb vibrational energy as a building sways, whether it be in wind or in earthquake. And basically they provide resistance to movement. That is, if there's a fast movement, they produce a lot of force. If there's very slow movement, they provide very little force.
Each damper in the Torre Mayor exerts well over £1 million of force. They were designed to allow the skyscraper to safely absorb a substantial amount of seismic energy which might otherwise have caused damage or even collapse of the structure. In Taiwan, also a high seismic zone, Taipei 101 is one of the world's tallest super skyscrapers at 509 meters. The damper system designed here, called a tuned mass damper, acts like a huge pendulum to counteract the sway of the super tall building, which occurs during earthquakes, and gives the building structural stability. At the Federation Tower in Moscow, the dampers principle is used to give stability to the super tall panoramic central spire, which will be a staggering 509 meters high when completed.
Built into the design of the spire here is a few levels of tuned mass dampers, which are basically relatively large masses hung from a certain length to create a pendulum. And then at the bottom of this mass, where the actual ball of steel is, it'll be driving piston dampers to dissipate energy. So as the wind is blowing and the mass tries to vibrate, it's building up energy within itself through this resonance. So to sort of damp out the resonance and damp out the energy, we have the mass swaying at the same period as the spire, driving these dampers, dissipating energy, and allowing the spire itself to not go into this aerodynamically unstable range of motion.
Disasters caused by earthquakes and structural weakness teach architects and builders important lessons in the design of super tall buildings. But it took a totally different kind of disaster to change their approach entirely. The attack on the World Trade Center in 2001, with its devastating loss of life, received more media coverage than any disaster in history. As well as transforming the political landscape, it also changed some of the fundamental principles of skyscraper construction.
It's led people to think much more about performance-based design and actually questioning and challenging what is right and what is wrong in a building, what is safe in respect to this building. I think it's that change in attitude that's certainly been evident from the post-9/11 era that's probably its biggest legacy.
When the Twin Towers were topped out in 1973, they were the tallest skyscrapers in the world, breaking new ground with their radical all-steel tube construction. However, with 9/11, the weaknesses of the design and materials would be fatally exposed. One of the first lessons learnt was that steel structures can be lethal when subject to intense heat. The tower's steel frames were designed without any masonry or concrete cores. Without these, it had very little effective fire protection. With an open plan layout, the fire had total freedom to spread rapidly. The steel beams failed from the intense heat, and without the support provided by these beams, the columns began to buckle. Like Ronan Point, the towers had only one load-bearing path. And with no alternative, the steels could not support the weight of floors above, collapsing onto them. An initial cave-in triggered a disastrous progressive collapse. But even before the towers collapsed, another fatal flaw in modern skyscraper construction was exposed. With their mechanical and electrical systems unprotected against fire and impact, the elevators in the Twin Towers were rendered unusable, and the stairs proved tragically inadequate for evacuation and rescue. Seven years on, work is progressing on rebuilding the World Trade Center site. The first skyscraper to be built at Ground Zero since 9/11 is 7 World Trade Center.
These were the footprints of the original Twin Towers, which are being designed and constructed in the new World Trade Center Memorial. Tower 1, the Freedom Tower, and Towers 2, 3, and 4 are modeled here, and we are in 7 World Trade Center, which is located right here.
7 World Trade Center is a symbol of America's resilience and determination to rebuild and assert itself as a world leader in skyscraper construction.
We learned on 9/11 about the reliability, the importance of reliability and redundancy of systems.
With an emphasis on safety, engineers here are surpassing New York's already stringent building codes.
We had to reinvent the codes to deliver the strongest building ever built.
At 7 World Trade Center, engineers have continued using steel. But crucially, they're employing an advanced protective coating to safeguard it from fire.
Now, this building fireproofing system, unlike most common fireproofing systems, is cementitious in nature. It has a cement content to it. And it also has a much greater adhesion to the steel and a cohesion within itself. And as you can see, it doesn't compress. So it's much stronger than common fireproofing. And the intention is to provide protection to the structure. It's very important that the fireproofing remain on the steel under emergency circumstances.
When Madrid's Torre Windsor skyscraper was gutted by fire in 2005, the steel structure, some of which had a similar fire-resistant coating, remained standing in spite of the intense heat and the fire blazing for a full 24 hours. The Torre Windsor had a reinforced concrete central core, able to resist the fire, which saved the skyscraper from collapse. It's the concrete core at 7 World Trade Center, with its 2-foot-thick walls, which is central to the idea of safety.
The center core is like the spinal column, supporting all of the other elements in the body. And this must be protected, as does the spinal column protect the nerves within the column. And so the reinforced concrete core houses and protects the essential elements of the building.
The designers behind 7 World Trade Center are determined that never again should people be trapped in a damaged tower with no means of getting out.
What you have to create is a building in what you can get out all the people that they are working on the building in a safe way to get them out, and then the building to have the minimal amount of damages.
Here, the essential escape routes of elevators and staircases are engineered within the reinforced core to protect them from failure and provide a protected passage for people to evacuate quickly and safely. They exceed even the tough new building regulations introduced in New York post 9/11.
The stairs are 1 foot wider than required by code. And the reason for that is that we wanted the ability for people to be able to walk down one side and someone else to walk down the other. So 2 people to walk side by side. The code requirements had the stairs much tighter than that and did not enable people to walk side by side or for there to be a counterflow of traffic. Some people going down the stair, perhaps emergency responders coming in the opposite direction.
With wide landings acting as refuge areas, people who can't evacuate immediately can wait, free of further danger, for the rescue services. The core also provides protection for the fire suppression system to mitigate against an interruption to the water supply in the event of a disaster.
Not only are they protected, but we have redundancy. We have one in each of the 2 stairs, and the sprinklers are hooked up to both of them. So in the event of a failure in this particular riser, there's never more than 1 floor without sprinkler protection.
As a direct result of the events of 9/11, engineers at 7 World Trade Center have rewritten safety standards that are now being adopted and surpassed all over the world. Since 9/11, engineers are using every technique at their disposal to future-proof their skyscrapers against disaster. In Moscow, those behind the new Federation Tower are determined that its design and construction will enable it to withstand any threat from any quarter.
Nobody ever thought that airplanes would crash into a building. Nobody ever tried to think about what would happen if all of the building's columns were simultaneously impacted, removing all the fireproofing that was on them, and then melted by an incredibly hot fire.
At the Fed, a state-of-the-art blast-proof facade envelops the building from top to bottom.
The fact that it is consisting of a laminated light. Laminated glass is 2 lights of glass with a sandwich layer in between. It's a PVB or polyvinyl butyl layer sandwiched in between 2 lights of glass applied by heat and pressure. That sandwich layer of glass allows it to be structural in nature, to span a taller distance than usual, in this case 4 meters, and also to react to large and small missile impacts. Small missile impacts and large missile impacts, the laminated units, glass units on the building are designed to absorb the impact of those missiles, but also to not become disengaged from the metal framing that holds them on the building.
Конструкторам было сделано техническое задание, было сделано предположение, что башня должна быть недосягаема для воздушных атак. Для этого конструировалось таким образом, чтобы выбивание как минимум одной колонны, соответственно, путем попадания любого летательного аппарата, никоим образом цельность башни не нарушала. В этом же контексте мы предположили, что в ближайшее время высотное здание и безопасность, как два слова, должны стать словами синонимами.
And the strongest card in the Fed's safety hand? Concrete. But no ordinary concrete. Specially designed super-strength grade 90 concrete. Capable of withstanding a terrifying impact of up to 1,200 kilonewtons.
The formula and the final concrete is extremely strong. And that's why to produce it, we built special factory. We use special laboratories who control the technology. We train the contractor to work with this concrete. It's extremely important and it's extremely fine-tuned job.
The steel encased inside this concrete will not suffer the same fate as the Twin Towers, one of which came down within 56 minutes of the fire catching hold. A central core with 1 metre thick walls of this super-strength concrete will provide ultimate strength against impact, as well as superb fire protection.
They're high-strength concrete, they're very thick. They're sort of like a sink for heat. And if you have such a huge volume of concrete where there's a fire next to it, it's better than having a very small volume of concrete. So the concrete would raise in temperature very slowly because it takes such a long time to elevate the temperature of concrete, of this much concrete.
This fortress in the sky is designed to be fire resistant for 4 hours at a blistering 1,200 degrees Fahrenheit. And the Federation Tower is aiming to rewrite the rulebooks on emergency evacuation. Whereas once it was don't use in the event of an emergency, a revolutionary twin elevator system encased within the fireproof core runs 2 carriages per shaft. These are designed to be used in an emergency and ensure people can evacuate quickly and safely.
9/11 changed the thinking in the elevator business, how to bring the people safe down and evacuate them, not to make the people nervous and not to say you have to take the steps. No, you can take the elevators.
The stairs are also housed within the reinforced core to provide a clear escape route, free from fire and debris. The access to these stairwells is protected by a drencher system, which acts as a water curtain.
Предназначен для того, чтобы задержать данное проникновение огня или дыма в данный путь эвакуации.
And for those who can't escape immediately, there are refuge areas located on the outrigger floors to protect them until help arrives.
The idea of the refuge floor is to give a few floors throughout the building, throughout the height of the building, that people can go and wait for the fire department to get them. So the fire department can actually use a couple of very well-protected elevators to come to these floors and bring them back down, whereas in the World Trade Center, the firefighters were running up the stairs all the way up 100 floors of stairs to try to rescue, as many people as they could. And as well, you can see this is a great place to put it because it's very structurally sound and just very safe.
All skyscraper designers now aim to create buildings that remain strong and stable under any condition, capable of resisting earthquake, fire, blast, or structural collapse. Some aspire even further, taking on what is arguably the most difficult challenge: how to overcome finite energy reserves in the creation and maintenance of super tall buildings.
Super tall buildings have the advantage of being above everything else around it, so they have greater exposure to solar radiation that can be converted into power. But they also have a density that allows you to employ technologies that would not otherwise be cost-effective if the building was more distributed and you didn't have that density of space.
With wind turbines, solar energy, and a unique water-cooled air conditioning system, the architects of the Pearl River Tower in China, due for completion in 2010, aim to make it among the most energy-efficient super-tall buildings in the world.
We look at how buildings can reduce their reliance on the city's electrical grid. We look to reduce the amount of water that they consume. We also look to take energy that is inside the buildings and recapture that energy and reuse it over and over again.
In Dubai, the proposed 322-metre high Burj Al Taka skyscraper would be entirely energy self-sufficient. Power would come from a 60-metre wind turbine on the tower's roof, from hydrogen extracted from seawater, and from 15,000 square metres of solar panels. In what would be a unique engineering feat, in Moscow and Dubai, there are plans for rotating towers entirely powered by giant wind turbines situated between each of 78 separately rotating floors. Engineering ambition knows no bounds. The Burj Dubai is the world's first mega high-rise. Already at 700 metres, it is the world's tallest structure. On completion in September 2009, it will be nearly 1 kilometre high. Tunnels, a miracle of modern engineering. They make mountains manageable, connect our cities, and can even bring together continents. Places of mystery and adventure, and occasionally, catastrophic disaster. Since the tunnel building boom of the 1960s, the world has become a very different place. More people, more trucks, more traffic, more accidents. The past decade has seen tunnel disasters that have spelt destruction, chaos, and even death.
Sie sind alle in den ersten 10 Minuten erstickt.
We all got out on the Italian side. The people on the French side were not so fortunate.
While investigators pick through the ashes to find out what went wrong, the engineers of new tunnelling projects figure out how to put it right.
We have to eliminate catastrophic failure.
Across the world, the modern tunnel is built from disaster. Tunnels bring people together, connecting towns, countries, and even continents. But the world's tunnels are under pressure. As more traffic and freight passes through them, accidents are on the increase. 1999, a burning truck was abandoned in the Mont Blanc tunnel that connects France and Italy. 39 people died. In 2001, a truck collision in the Gotthard tunnel caused a massive fire. 11 people died. 1996, a burning cargo train caused the lining of the Channel Tunnel to explode. Serious structural collapse.
They said that the concrete was falling on them like shrapnel.
From each event come crucial lessons in tunnel design, revised approaches to evacuation and fire control, new construction techniques to prevent tunnel collapse, fresh ideas about accident prevention. Across the world, new tunnels are being built from disaster. One of the most innovative new tunnelling projects is the Marmaray Tunnel, under construction in Istanbul, Turkey. At an estimated cost of $3.5 billion, the 13.6-kilometre-long tunnel system will run 58 metres under the Bosphorus Straits. It will be the deepest immersed tunnel in the world. Istanbul needs the tunnel badly. It has a population of 12 million and terrible traffic problems. It will take the pressure off the Bosphorus Bridge and will be the first tunnel connection between Europe and Asia.
The Marmaray project will make the lives of the Istanbul citizens more comfortable and will save them a lot of travel time.
The tunnel's designers have much more to consider than commuter comfort and reduced journey times. Their biggest challenge, as for any tunnel construction, is how to overcome fire, a tunnel's single greatest threat, as recent disasters have shown. On March the 24th, 1999, 2,000 kilometres away across Europe, a sequence of events began to unfold that was to have fatal consequences and would influence the design of all new tunnels to come. At 10:46 in the morning, a heavy goods vehicle entered the 11.6-kilometre-long Mont Blanc tunnel, which connects France and Italy. 6.7 kilometres inside the tunnel, the driver was shocked to discover his truck was on fire.
J'ai regardé mes rétroviseurs et j'ai vu de la fumée du côté droit. Je suis sorti du camion, et la fumée était déjà beaucoup plus importante. J'ai voulu prendre l'extincteur, mais je n'ai plus eu l'occasion parce que ça a éclaté en feu, toute la cabine.
The driver abandoned his vehicle and managed to escape, but he left behind a disaster in the making. A burning truck with a highly flammable cargo. One of the drivers also using the tunnel that day was British trucker John Whitby.
In a period of 18 months, I probably used the Mont Blanc about 40 times. It was a dark, depressive type of tunnel. It seemed to go on forever.
Whitby entered the tunnel on the Italian side, en route for France.
I was driving for about 5 minutes into the tunnel, and then we started to get traffic approaching that was flashing its lights.
Moments later, around 40 vehicles were forced to a halt, including Whitby's truck.
We stopped, we got out of the vehicles, and we were looking down the tunnel to see what was going on ahead, whether it was roadworks or whatever, and it was all black. So we just assumed that the lights had gone out further down the tunnel.
Within minutes, the Italian emergency services began to arrive.
The fire brigade came roaring into the tunnel, and they shot straight past us, sirens going, and just disappeared into this wall of blackness. And it was only about then that we started to think, well, that black might just be smoke.
The abandoned truck was carrying margarine, highly flammable, and by now burning hot and fast. As the tunnel filled with smoke, there was a series of loud explosions.
Like a field gun in the distance. We've got a fire on here. There's that's truck tyres exploding. The entire tunnel actually shook. The road shook under the feet. You felt the air vibrate and the walls shake.
Whitby and others near him were rescued by an Italian fire engine, forced into retreat as the fire escalated.
And we all got out of there at a very rapid rate of knots.
Those nearer the French exit were less fortunate. The smoke surged towards France, stopping the French fire team from entering.
Et à leur arrivée, il y avait déjà plusieurs kilomètres de tunnels enfumés. Et les premiers intervenants ont été bloqués dans le tunnel.
The drivers on the French side of the blaze were trapped, enveloped in thick smoke.
The lucky ones died in the cars. They probably 2 lungfuls of the smoke and they were dead. It was that toxic and that thick.
Some drivers on the French side managed to leave their cars for the supposed safety of the tunnel's fire refuge cells. But these were designed to deal with a small car fire, burning at 800 degrees centigrade for only a few hours. At Mont Blanc, the fire blazed at 1,000 degrees centigrade for 53 hours.
And these poor people were basically cooked inside the safety cell. And I honestly cannot think of a worse way to die.
It took 5 days for the tunnel to cool down before the fire services could enter. They were horrified by what they found.
Pour l'incendie du tunnel du Mont Blanc, il y a eu des températures jusqu'à 1000 ou voire 1200 degrés qui ont été atteintes dans certains secteurs du tunnel. Et donc, en arrivant sur les lieux du sinistre, après avoir refroidi la voûte, nous avons découvert progressivement plusieurs dizaines de véhicules totalement calcinés, hein, puisque, je le répète, les températures sont montées à plusieurs centaines de degrés, voire à 1000 degrés. Donc, des restes de véhicules, de tôles, de carcasses de véhicules sur plusieurs centaines de mètres de long. Et notamment sur 600 mètres, même l'asphalte de la route avait fondu et brûlé.
Of the 50 people caught in the fire, 39 died.
When I think back now, I was probably one of the 11 luckiest people in the world. It's an experience that will never ever leave me, because those people shouldn't have ever died. None of them should have died.
The Mont Blanc fire was a tragedy that drew worldwide attention. An investigation began into what had gone wrong. Part of the answer lay in changing times. Built in 1965, the Mont Blanc road tunnel was designed to carry light traffic, not heavy goods vehicles. Wind forward to the late 1990s, and a different world uses the tunnels of Europe. Part of this new economic order is the container truck, often carrying flammable materials. The old Mont Blanc fire refuges and ventilation system simply couldn't cope with the intensity of a modern truck fire. Since 1999, the Mont Blanc tunnel has been redesigned and refitted along its entire length. When the truck caught fire, smoke and toxic fumes rapidly accumulated in the tunnel, with catastrophic consequences. As atmospheric pressure was lower on the French side than the Italian side, the smoke surged towards France. The Italian control center switched on the fans to blow the smoke through, but instead of clearing it, they simply fed oxygen to the fire, making it burn hotter and faster. The tunnel's refit has adopted an innovative system, which it's hoped will prevent history ever repeating itself. 116 new ceiling fans have been fitted along the tunnel. The fans maintain an area where wind speed is 0, the point depicted by the yellow line. This 0 wind speed zone can be manipulated remotely to control the movement of smoke. In the event of a fire, the fans direct the still zone to the area of the blaze, allowing smoke and fumes to be removed through extraction vents by powerful ventilators. At the same time, the new ventilation system brings fresh air into the tunnel.
In this very large technical room, you have two kinds of turbines. You have on my right hand, you have the blue one in place to pump the fresh air from outside and to push it inside the tunnel. So fresh air is very cold and they don't need special protection. But here you have the red turbines. These turbines are protected. They are here to extract the smoke and extract the hot air in case of fire inside the tunnel.
With the smoke under control, the rebuild addresses the provision for refuge and escape. The old fire rooms along the edge of the tunnel were death traps, quite unable to cope with the ferocity of a high-intensity blaze. The escape system has been entirely rebuilt, with new safety shelters capable of withstanding heat up to 1,000 degrees centigrade for 4 hours.
Okay, I'm entering now in the safety shelter. The safety shelter is a place where you are completely safe. The only thing you have to do is to wait for further instructions. And the further instruction will come through this video system. And through this video system, I'm able to enter in contact with the operator. I push.
Hello?
Bonjour. We are in the shelter number 16.
Yes, you are there and now you wait there.
Okay.
Our rescue team will be arriving in 2 minutes.
Okay. So the operator said me that I have to wait here for the rescue team, and the rescue team will come through this door.
The key innovation in the new rooms is that this time they're connected to an escape tunnel that leads to the French and Italian exits.
To the escape corridor, and you follow me. Normally, the rescue team will open the door, and we are now under the way, and you have Italy here and France here.
The new Mont Blanc tunnel is an old structure that has been rebuilt, but it will never be risk-free.
We will never say that. We did the maximum to avoid terrible consequences to an event. But nobody can say that we will never have an event in the tunnel.
180 kilometers away in Switzerland, the brand new Loschberg tunnel has also learned lessons from the Mont Blanc road tunnel disaster. Opened in 2007, it's a dual-bore rail tunnel. The escape system here is on a grand scale, capable of dealing with 1,500 passengers. Loschberg is the third longest tunnel in the world at 34.6 kilometers long, 3 times the length of the Mont Blanc tunnel. To cope with the size, here the ventilation system is colossal, built to deal with a high-power fire reaching 1,000 degrees centigrade.
So we're here in the ventilation center of the Loschberg base tunnel. There are 2 such centers, one here, one 50 kilometers north, with 2 ventilators. Each of them can pull 200 cubic meters of fresh air into the tunnel system. This ventilation system is crucial for the security in the Loschberg tunnel. It's used to take out polluted air in case of a fire from the railway tunnel tubes and takes it outside. Here we see how fresh air from outside is brought through these noise-reducing walls into the ventilator and is pushed with force into the tunnel. It's now running only at 25% of its capacity. In case of an emergency, if it would run full speed, it would burst our ears. But now it's quite quiet, that's why we can still talk.
Loschberg also addresses the need to get the emergency services in as quickly as possible. At Mont Blanc, the firefighters were obstructed by the heat, smoke and darkness. Here, the system boasts the ultimate in early response, the fire train.
Also bei einem Alarm, Brandalarm, wird es 5-6 Minuten gehen mit beiden Wasserwerfern. Und dann lassen wir knappe 5000 Liter raus und haben 50 Kubik dabei, also das ist relativ schnell, wäre es leer.
The train isn't just about fighting fires, it's also a mobile hospital.
Der Zug zu trennen in Löscheinheit und Rettungseinheit. Mit der Rettungseinheit können wir einen Shuttle-Betrieb machen. Also das heisst, wir können Leute aus einem Gefahrenbereich rausbringen
But even this system has limitations. In the most intense heat, above 1,000 degrees centigrade, there's little even the most rapid response team can do.
Und dort ist das Limit ganz sicher Hauptaugenmerk auf den Menschen. Was kann der Feuerwehrmann oder Frau, was können sie noch schaffen? Können sie noch schaffen oder gar nicht mehr? Und dort ist die Limite. Dort muss man dann auch den Mut haben und sagen, es ist nicht mehr bekämpfbar und den Rückzug nehmen.
In Turkey, the Marmaray project has taken the lessons from Mont Blanc to the extreme. Although this tunnel will be relatively short, just 1.5 kilometers between the stations on either side of the Bosphorus, its ventilation system will be the most powerful in the world. And this is where they're going to put it. The Serkeci Deep Station. This massive ventilation chamber is only a small part of the huge station complex under construction. Chief Engineer Melir Babur is in charge of the design of the ventilation systems.
Okay, we are at the west ventilation shaft of Sirkeci station. The total shaft length is around 200 feet.
As always, the key to any ventilation system is to have control over the smoke in the tunnel.
And we want the smoke to move in a certain direction so we can have the passengers evacuate in the other direction. This is the main purpose, okay? There are going to be about 7 different levels, equipment levels, and each level will contain different equipment. Most of them are dealing with the emergencies, like tunnel ventilation funds will deal with emergency situation. The main purpose here is to reduce the risk of fire, and when the fire starts in that unfortunate case, to put aside the adverse effect of the fire.
As in Loschberg, there will be ventilation plants at each end of the tunnel, one in Europe, the other in Asia, with one set of fans sucking air out, the other pushing it through. The lessons of the Mont Blanc disaster were swiftly learnt and rapidly implemented. But despite this, only 2 years later, another Alpine tunnel disaster was to horrify Europe. The Gotthard Road Tunnel connects Switzerland and Italy. When it opened in 1980, unlike the Mont Blanc Road Tunnel, the Gotthard Tunnel was already equipped with a state-of-the-art fire detection and evacuation system and was considered the safest in Europe. But refuge cells constructed every 250 metres of its 16.4 kilometre length and an advanced tunnel ventilation system weren't enough to prevent the tragedy to come. On October the 24th, 2001, 2 lorries travelling in opposite directions collided 1.5 kilometres from the Italian entrance. A ruptured fuel tank immediately ignited. Vehicles travelling in both directions on either side ground to a halt. Urs Gerber was caught in the jam.
Coincé, donc j'ai arrêté le moteur. Je suis sorti et puis je suis allé contre la mur, donc direction nord. Et là, tout d'un coup, c'était sombre.
As the fire took hold, wheels exploded in the heat and toxic smoke filled the tunnel.
J'entendais des petites cris et puis des petites explosions, mais à ce moment-là, c'était comme, faut dire, comme un rêve. Alors je voulais pas mourir, et puis pourtant je sentais que j'arrive plus à respirer comme il faut. Donc.
Gerber and 4 other drivers couldn't find the escape room, and the air was running out. They were trapped.
Pas plus, donc, parce que c'était seulement la volonté de survivre qui m'a tenu en vie.
By chance, one of the group managed to locate an exit.
Il a ouvert la porte, et puis à ce moment-là, c'était clair, et puis on était sauvés, on peut dire. Hein.
Not all the people caught in the tunnel were as lucky as Gerber. Walter Steiner was tunnel controller on the day of the fire.
Es gibt Chauffeure, die sind mit dem Rauch geflüchtet und konnten den Schutzraum noch erreichen. Und das haben aber nicht alle geschafft, sondern sie haben den Eingang zum Teil nicht mehr gefunden oder sind zum Teil im Fahrzeug geblieben. Sie sind alle in den ersten 10 Minuten erstickt aufgrund der toxischen Rauchgase.
In all, 11 lives were lost. After the tragedy, steps were taken to improve the emergency lighting system, making it easier to find your way through dense black smoke. But shocked that lives were lost, despite the state-of-the-art systems already in place, designers now focus their attention on trying to prevent accidents happening in the first place. One innovation was to monitor and control the volume of heavy goods vehicles entering the tunnel at any one time. An automated system was put in place to drip feed a maximum of 3 trucks per minute into the tunnel. Using a traffic information collector, operators not only monitor the speed of vehicles, they ensure that vehicles are kept apart.
Nach diesem Unfall hat man versucht, mit einem System die Lastwagen auseinanderzunehmen, wenig oder größere Abstände zu bilden.
Before the accident in 2001, there were 45 vehicle fires in the tunnel every year.
Heute mit dem System sind es nur noch 10. Also 10 pro Jahr.
The Gotthard team went a step further. They wanted to solve the problem of how to prevent spontaneous combustion of the sort that had caused the catastrophic fire at Mont Blanc. At the Gotthard tunnel, a new technology is being introduced that will combine 3-dimensional thermal imaging cameras with the traffic control system.
This object you see is car transporter. You can measure this object, you can do everything with it. This is the base for all our applications.
The next step is to take a thermal scan and drip it over the 3D object.
We see here that it's a hot spot here at the end of the vehicle. Whenever we see, okay, that's the one which we think it's too hot, and then the operator has to react. And he has to go on and has to pick it up out of the traffic. In the Gotthard Tunnel, there are multiple fires every year. We can reduce this number of fires by 80%. Then we have a huge advantage.
Through traffic control and early fire detection, it's believed that the Gotthard Tunnel will be less exposed to another killer fire. In recent years, many of the big tunnel fires resulting in loss of life have been in a road tunnel. Vehicles, and especially large vehicles, trucks and lorries, are travelling bombs primed with fuel, sometimes carrying highly volatile cargoes, subject to spontaneous combustion and vulnerable to driver error. One answer to some of these issues is to completely replace road with rail. The new Marmaray project in Turkey is a rail tunnel. All freight will be carried by train, not by truck. 2 separate tunnels, one in each direction, prevent the risk of the trains colliding. And by eliminating heavy goods vehicles altogether, the tunnel's designers have taken on the lessons of previous disasters. But even train tunnels can be plunged into chaos by major accidents. In 1996, the Channel Tunnel that connects England and France revealed a frightening weakness in its design. It was the most advanced rail tunnel of its type, built as 2 tubes with a separate rescue tunnel and crossings at every 300 metres. It was thought to be the safest tunnel in the world. It runs through the chalk seabed that lies under the English Channel, connecting England and France. At 9:48 p.m. on the 18th of September, a Eurotunnel cargo train entered the Channel Tunnel at Sangatte, near Calais, northern France. On one of the trucks in the cargo section of the train, a fire was smouldering. The fire spread to the train, and 19 kilometres inside the tunnel, it suddenly stalled. The blaze was soon out of control. In the smoke-filled darkness, the train's 33 passengers and crew were led towards the safety tunnel by the fire services. It was a narrow escape.
We couldn't see because the smoke was getting into our eyes.
I thought I was going to die, I really did. I was laying on the floor, everything was going, lightheaded. I thought I'm going to die here.
The passengers were safely evacuated, but the fire couldn't be controlled. It had already reached critical temperatures over 1,000 degrees centigrade. The concrete tunnel lining began to spoil, falling away in huge chunks. At the heart of the fire, the lining was almost completely lost. Luckily, the tunnel was running through a dry part of the seabed. If there had been water on the other side of the lining, there would have been a catastrophic flood. Professor Gabriel Alexander Coury of Imperial College London has studied the 96 Channel Tunnel fire.
Half the section was destroyed, and in some parts, the spalling took place all over the section, right up to the ground. Now, that is structural damage. 500 meters of the section was damaged, of which 50 was serious, and that is in terms of the explosive spalling of concrete.
The tunnel was lined with high-strength concrete, where additives like fly ash create stronger chemical bonds in the concrete mixture. At the same time, the amount of water is reduced, which also increases strength. But in the Channel Tunnel fire, even this small amount of water became a hazard, turning to steam in the intense heat. The water pressure rose as high as 100 times atmospheric pressure.
The steam pressures will build up faster than they can be diffused, and there is a risk of an explosion taking place.
In the high temperatures, the lining of the tunnel literally blew itself apart.
And the firefighters in 1996, they said that the concrete was falling on them like shrapnel.
After the 1996 fire, Eurotunnel repaired the damage using the same high-strength concrete lining. But they upgraded their fire and rescue services in the tunnel, a strategy that withstood the test of another serious fire in 2008. Even though this type of concrete is now known to explode in intense heat, it's still in use in tunnels across the world. Some tunnels, like the Loschberg Base Tunnel, are immune to the threat of collapse. Because of this, the Swiss Alps, made of hard granite.
We have a stable rock structure, so there's no risk of a breakdown of the tunnel. Even if this concrete here would burn down or break, the tunnel would not break down completely. So this is a risk that we can almost exclude.
But 2,000 kilometers away in Istanbul, the Marmaray Tunnel doesn't have the protection of granite. It's lined with high-strength concrete, but lessons from the Channel Tunnel fire have been taken on board.
In the history, there are that sort of accidents which happened both in the highway tunnels and also the railway tunnels. And Channel Tunnel fire is one of the most serious examples in the past. So based on that, of course, we took lessons.
The concrete used to line the Marmaray Tunnel is protected with a fire insulation layer.
And there will be an application of fire insulation material depending on the ground conditions, the rock quality, whether we are in the fracture zone, the groundwater level, because we have to eliminate catastrophic failure and we have to prevent flooding.
The tunnel boring machine is a 150-metre-long complex that removes the rock debris from the drilling face at the leading edge of the tunnel.
We are at the end of that TBM5. We have, as I have mentioned, excavated 2 kilometers until now. And you may see that cutter head, which is the main part of the TBM machine you see there. These are the pistons which are located at the periphery of that cutter head, which has on the order of 75,000 kilonewton thrust force, which pushes the ground like that. So this machine is manufactured specifically for Marmaray project, considering all the soil conditions, the strength of the rock, etc. We will connect to the IMT the element number 11 at the Asian site. So the IMT element and TBM will connect to IMT. We will do all these water insulation works and the inner concreting works, and at the end we will be able to have the full tunnels under the Marmaray project.
Fire is not the only threat to the structure. This huge tunnelling project is only 10 miles from the North Anatolian fault line. For Deputy Project Manager Hussein Belkaya, structural failure and flooding of the tunnel due to earthquakes is a very real hazard.
The occurrence of a big-scale earthquake in the next coming 30 years in Istanbul is 62%. This is really very high percent.
Like the Channel Tunnel, the Marmaray Tunnel runs through the seabed. Flooding is a real and potentially catastrophic risk. It's a threat that was brought vividly to light 2 years into construction. At one of the stations that will link the tunnel system together, they unveiled the remains of the ancient harbour of Byzantine Constantinople. Complete with 32 warships, this was one of the greatest archaeological discoveries in Turkey's history. For archaeologist Doğan Perinçek, the dig also offered up an environmental warning from history.
This excavation area has many chapters. And within this marshy sediments, we have some sediments related to flooding. What caused this? What's the reason of this?
For Doğan, the key to unlocking the mystery lay in the historical records of Byzantium. In the 6th century, there had been 3 major earthquakes, and the new evidence of flooding pointed to one of earthquakes' lethal side effects: tsunami. 1400 years ago, a giant wave had devastated the port.
Earthquake during the 6th century and related to tsunami destroyed many things in the region. And the part of the harbor destroyed, and also wall of the city destroyed. And same tsunami destroyed the piers located within the harbor.
Tsunami modelling suggests the wave was between 6 and 8 metres high and had struck the port right where a crucial element of the tunnel was now being planned.
They are going to build a station here. And entrance of this station should be 6 or 8 meters higher than present-day sea level. Otherwise, will be disaster.
The tunnel's designers took their history lesson to heart and raised the height of the station entrances to protect the build against a future tsunami.
We have to be very cautious, and we have to take a lesson from the past.
In a dry dock 40 kilometres from the Bosphorus, the 11 segments that will connect east and west are being constructed. A single segment weighs 18,000 tonnes, and at around 150 metres, each one is longer than a football field. The tunnel is itself designed to absorb the impact of an underwater earthquake, measuring up to 7.5 on the Richter scale.
Şu anda üzerinde bulunduğumuz tüp elemanı, boğaz tüp geçiş elemanlarının içerisinde sonuncusudur. En sonuncusu bu eleman, 11 numara. Boğazda batırılan bu parçalar, boğazda şu elemanlar aracılığıyla, şu contalar aracılığıyla birbirine bağlanıyor. Birbirine sızdırmaz hale geliyor. Ve ortaya çıkan bu 1400 metrelik tünel hattının sismik jointleri var giriş ve son uçlarında. Dolayısıyla bütün bu sistem depremde yarım metre hareket edecek şekilde inşa edilmiş olmaktadır.
Inside this segment, Adnan makes some last-minute checks before it's submerged. It will be floated into position above the drop location, where a series of ballast tanks will be filled to sink it to the seabed. For Adnan and his team, this isn't just a piece of engineering, it's an historic moment.
Böylece İstanbul Boğazı'nın altından ilk kez bu büyüklükte bir tünel, bir geçiş sağlanmış oldu. Bu belki 200-250 yıldır insanımızın bir hayaliydi. Bu gerçekleşmiş oldu.
Tam bu nokta işte bu tüneli Avrupa tarafına bağlayan ucudur.
In addition to seismic joints, the tunnel designers have ensured that the tunnel will not be damaged by liquefaction. Geologist Dr. Orhan Simcek has identified the problem areas.
This is a geological longitudinal profile of the Bosphorus channel along the immersed tube alignment. This is sea level, this is seabed level, this is rockhead level, and this is immersed tube alignment. The yellow color, soft clay material, call it golden horn clay. Towards east, Üsküdar side, immersed tube foundation is made up of sandy material. During high seismic event, there is a risk of liquefaction potential.
The Asian side of the tunnel lies in sandy soil. An earthquake would be disastrous.
It is estimated that fault rupture in the same segment happen between 200 and 300 years, recycling. So the last major earthquake in the center of the Marmara Sea happened in 1776. So you come to the States. So it is a high probability to have a major earthquake during the service life of this project.
The solution is simple: to surround the tunnel in a coarse gravel lining. The dredging vessel is busy day and night. The gravel will insulate the tunnel from seismic shocks.
In order to avoid the liquefaction risk in the sandy soil, you have to drain the soil. To drain the soil around the tunnels, immersed tunnels, coarse-grained crushed stone is required to have voids to release the pore water pressure during the seismic event.
When a serious earthquake eventually strikes, the large voids in the coarse gravel cladding around the tunnel will release the pressure build-up, protecting the structure. Simple, but effective.
This relaxation of the pore water pressure will prevent damage from the earthquake.
The Marmaray project is in the final stages of its construction. Many of its fundamental design features will have been informed by past disasters. Post the Channel Tunnel collapse, the Marmaray project will be protected from fire by a layer of thermal insulation. From the Mont Blanc fire comes the most powerful ventilation system in the world to control smoke. And the archaeological lessons of history bring a system of seismic joints to resist the effects of an earthquake. Above all, the Marmaray system's engineers are determined to eliminate truck driver error. Under the Bosphorus, 2 parallel rail tunnels will carry only high-speed trains. Truck shuttle trains will eventually pass through the tunnel, but trucks with flammable loads have to cross the Bosphorus by ferry. Despite all the challenges to construction, the tunnel project is back on track and due to open in 2012. 10 of the 11 tunnel segments have now been laid. At a depth of 58 metres, the tunnel has to be able to withstand 6 times the atmospheric pressure at sea level. For the Immersed Tunnel project manager, Hideki Sakaide, the tunnel is a new silk route between Europe and Asia.
Then we are now walking towards the European side. So we can say now we are walking in the new Silk Road.
The East and West are almost connected. Tunnels are on the brink of a new era. In many countries, a new movement has begun that aims to use tunnel technology, not just to connect people and places, but to construct whole new worlds underground. Amsterdam in Holland is one city fighting a very modern battle for more space. The city is in crisis. If cars are prevented from entering the historic city centre, the local economy will die. If the crowding continues, the city could become a polluted wasteland. Civil engineer Bas Obladen has a vested interest in solving the problem.
I was born in Amsterdam, and when I was young, that's so 60 years ago, it was a very nice town to be and to live there, and the quality of life was also very nice in those days. And say 8 years ago or so, I went with my son. I said, I show you the places where your father have been born and where he lived. I was shocked about what I saw. Everywhere there were cars and bikes, and it was terrible in my opinion.
Baz's vision is to remove cars from the roads and canal sides. And using tunnelling technology, take them below ground.
If the cars are, say, under the ground at the moment, then you get fresh air above the ground. So people are living longer, the quality of life is very nice. And alongside the canals, there are no cars.
The idea is to funnel traffic from the ring road into an underground network of tunnels. Amsterdam's canals provide the blueprint.
We have a lot of canals in Amsterdam, so I'm using the canals for a road under the canals, from the ring road to the underground system.
But tunnelling in Amsterdam is technically challenging.
The main problems in Amsterdam is, of course, the water level.
The engineers on the current north-south tunnel dig under Amsterdam are developing techniques that will help realise the new project.
Our main challenge in this area is the softness of the soil. We have to try to maintain a stable environment for the drill to go through. So what we do is we drill 90-meter long poles that will be used for a brine solution that will cool down the entire soil and thus creating a frozen, like a permafrost layer through the total width of the two drilling machines.
As the technology has developed, so has the ambition.
The idea is not to make tunnels to a destination and then connect different destinations. So we say if you build a connection, why not make it a useful space? So it's all about really making a very big space. It's like the doubling of the floor space which is in the center of Amsterdam.
The design would not only provide much-needed parking, massive underground spaces would house cinemas, squash courts, and even swimming pools. Those behind the Amsterdam project are conscious that whatever the space is used for, safety lessons from past tunnel disasters still have to be applied.
For the fire safety, we are really looking into the possibilities of compartmentation and that you are always within a reasonable amount to walk to a safe place. So if something happens in your vicinity, you can hold your breath and how many meters can I walk? Well, there would be a door. That is basically where we start from. And there are now materials which can really keep the fire on the other side of the doors.
For now, the Amsterdam dream of building urban spaces below the city streets is in the early planning stages. But in Turkey, the Marmaray Tunnel project is fast becoming a reality.
It is always difficult to construct a mega project in a urban, densely populated area. But once it is in operation, Marmaray project will save a lot of travel time and make the lives of more than 1 million passengers per day more comfortable.
Throughout its lifetime, the Marmaray Tunnel will face a double jeopardy of fire and seismic shock. High-speed trains are an essential part of the way we travel today, slashing journey times between major cities and bringing us in comfort to our destinations. But with our need for speed comes vital concerns about passenger safety, because when fast trains crash, the consequences can be catastrophic.
One of the most feared events in the rail industry is a runaway train, and this was one.
High-speed collisions can be explosive.
Es waren natürlich ganz schreckliche Momente für mich. Es ging dieser Lebensfilm durch den Kopf.
And the twisted wreckage of a crashed train is always a haunting sight for those who built it.
Donc, je dois vous dire que chaque fois que l'on a un accident dans le ferroviaire, on est pris comme ça.
So engineers always study a disaster with forensic scrutiny, analyse critical mistakes, and devise new technologies to prevent tragedy from striking again. Quite simply, every new train under construction is being built from disaster. In April 2007, the world train speed record was broken in France with a lightning speed of 574.8 kilometers per hour. That's 200 kilometers faster than the takeoff speed of a Concorde. But when trains carry so many people at such great speeds, if there's a fault with technology, lives are at risk. In 1998, a German express train collided with a bridge, killing 101 people. In 1988, a runaway train with failed brakes smashed into a stationary train at the Gare de Lyon in Paris, killing 59. And in 1979, in the small Scottish town of Invergowrie, an express train continued through a stop signal, causing a collision that left 5 dead. These crashes and many others over the years have brutally exposed flaws in safety technology and infrastructure, flaws that the designers of new trains are striving to eradicate. Meet the AGV. Set to roll out for commercial use in 2011, the AGV will be a modern titan of transit for the 21st century. It aims to carry French passengers in safety and comfort, distances of up to 1,000 kilometers in under 3 hours. That's the entire length of their country from top to bottom. A journey that would take 10 hours by road. The AGV is set to revolutionize the future of high-speed rail travel. The man behind this project should know. He's been in the business over 30 years. François Lacote, Technical Director of Alstom Transport, is widely regarded as the godfather of high-speed rail. And this is the prototype of his new creation. For Lacote, the AGV isn't just a train.
Ce prototype a un nom, il s'appelle Pégase. Pégase, dans la mythologie grecque, c'est le cheval ailé, c'est-à-dire c'est l'objet qui est à la fois terrestre mais déjà un peu aérien avec la vitesse, donc c'est Pégase.
Pégase has been spreading its wings on a test track in the Czech Republic, and for months an onboard team of highly skilled train engineers have been monitoring its every move, because these people know what can happen if they don't get it right.
Nous prenons toujours en compte, nous analysons tous les événements, les incidents, les accidents, de manière à faire profiter toutes nos conceptions nouvelles de cette expérience. Nous apprenons continuellement.
The AGV is a product of years of rail disaster analysis, disasters such as the world's worst ever high-speed rail crash. On June the 3rd, 1998, in the small German town of Eschede, Intercity Express train, or ICE, number 884, was on its regular route from Munich to Hamburg. The ICE travelled at 200 kilometers per hour and had an unblemished safety record. On this day, 287 passengers were on the train, among them Udo Bauch, who boarded at Hanover Station.
Meine Frau hat mich an diesem Tag um 9:05 Uhr an den Bahnsteig gebracht. Dort bin ich in den ICE eingestiegen. Ich saß im zweitletzten Abteil, erste Klasse, und habe im Abteil mich auf eine Tagung vorbereitet mit meinem Laptop.
It seemed a perfectly normal journey for Udo Bauch and his fellow passengers as ICE 884 travelled on towards Hamburg. But about half an hour in, passengers in the front car began to notice unusually heavy vibration. And then a piece of metal broke through the floor. Although the train now felt dangerously unstable to the passengers, the problems went unnoticed by the driver, who continued at top speed. As the train travelled on another 5 kilometres, passengers attempted to alert him. But it was too late. The train suddenly derailed, smashing into the supports under a road bridge.
Eine Vorwarnung hatte ich nicht. Es hat auf einmal einen Schlag getan, wo ich noch nie im Leben erlebt habe. Es ging auch sehr, sehr schnell. Es hat mich in Sekundenschnelle im Zugabteil umeinander geschlagen, von links nach rechts, von oben nach unten.
The impact of the collision caused the bridge to collapse. As the train jackknifed, 300 tons of concrete came down on top of it. Hundreds of passengers were trapped inside the crushed carriages. As the dust settled on the twisted wreckage, local policeman Andreas Effenhausen was one of the first on the scene.
Als wir hier ankamen, haben wir nur diesen kaputten Zug gesehen, völlig zerstört. und ansonsten gar nichts. Es war nicht zu hören. Ja, mein erster Eindruck war natürlich, dass ich wahrscheinlich aus dem Zug keiner lebend rausgekommen ist, so wie das aussah. Dass es wohl eine hohe Anzahl von Toten geben würde.
Although there seemed to be little sign of life amid the carnage, Effenhausen set out in a search for survivors.
An einem Punkt, da habe ich gestanden, habe da reingeschaut und habe aus irgendwelchen Gründen, die ich heute nicht mehr weiß, Hallo gerufen. Und dann hat mir jemand geantwortet und das war der Udo Bauch.
In the crumpled wreckage that was the second to last carriage lay passenger Udo Bauch. Amazingly, he was still alive.
Ich habe mich kurz nach dem Aufprall wiedergefunden, dass ich eingeklemmt war. Ich habe gemerkt, mein linkes Bein war eingeklemmt. Ich lag am Boden, im Zugabteil am Boden und habe natürlich sehr, sehr starke Schmerzen gehabt. Und das waren natürlich ganz schreckliche Momente für mich. Es ging dieser Lebensfilm durch den Kopf, wo ich an die Kindheit gedacht habe, an die Familie. Und das war schrecklich.
Für mich so ein Wunder, dass überhaupt jemand geantwortet hat. Und das hat so auch so ein bisschen die Lebensgeister in einem geweckt, das muss man so ganz ehrlich sagen. In dem Moment wurde ich auch dann richtig aktiv und habe versucht, von den mittlerweile hinzugekommenen Rettungskräften irgendwelche zu erwischen, die dem Udo da helfen und ihn da vielleicht rausholen.
Although seriously injured, Udo Bauch was eventually freed from his mangled carriage, but many others were less fortunate. 101 passengers died in what remains the deadliest high-speed rail crash in history.
Der Unfall von Elstede veränderte mein Leben total. Ich bin als kerngesunder junger Mann in den Zug eingestiegen, habe mich auf eine gute Beförderung verlassen und bin als Schwerbehinderter hier rausgekommen, kann nicht mehr arbeiten, kann viele Dinge des täglichen Lebens nicht mehr machen. Insofern hat es mein Leben total verändert.
Engineers were determined to find out what had caused this devastation. Finding the answer would be essential for the future of rail safety. It was clear that something had gone catastrophically wrong in the minutes before the crash. Investigators found the first clue on the front carriage. It was discovered that one of the rear wheels had failed and was left bent and broken. More clues were found on the track stretching back from the crash.
They found that there was damage to the track for quite a long distance, suggesting that there'd been at least a partial derailment.
But what had caused the wheel to derail at such high speed? As investigators continued to examine the track, the next piece of the puzzle fell into place.
5 kilometres back from the accident site, they discovered shards of rubber, which they determined had come from dampeners on one of the train's wheels.
To learn more, investigators turned their attention to the construction history of the ICE train. 7 years earlier, test runs had identified a problem with the train's monoblock wheels. Made from a solid single cast of steel, monoblock wheels were standard on high-speed trains at the time, but they caused serious vibration in the ICE's carriages.
Ich habe selber bei einer Fahrt oder bei 2 Fahrten mit dem entsprechenden ICE die Vibration in einem solchen Wagen, der solche unrunden Räder hatte, gespürt. Das wirkte auf die Bauchdecke und führte zu einem Erbrechensgefühl, sodass die Passagiere beim Erreichen einer bestimmten Geschwindigkeit bei diesem Zug schlagartig die benachbarten Wagen aufsuchten und nicht mehr in diesem Wagen sitzen wollten und konnten. Die Vibration bei den Passagieren und deren Unwohlseingefühl musste behoben werden durch eine neu einzubauende Komponente.
Fearing a huge loss of revenue from passengers unwilling to ride on such noisy and uncomfortable trains, the ICE's operators, Deutsche Bahn, urgently looked for a solution. They found what they thought was the answer on a tram. Trams had been using rubber-cushioned resilient wheels for years to reduce noise and vibration. Unlike the monoblock wheel, the resilient wheel consists of 3 parts: a central steel core, rubber pads to dampen vibration, and a steel rim mounted on the rubber.
These so-called resilient wheels are able to flex slightly and therefore absorb noise and vibration, and been used very successfully and for a long time on low-speed applications, particularly city trams. But to extrapolate their use to high-speed trains was a big step.
In their choice of the resilient wheel, engineers had solved the immediate problem of ICE's passenger comfort, but they'd unwittingly created a new problem. Resilient wheels were safe on relatively low-speed trams, but they had a much greater chance of severe metal fatigue at high speed than solid monoblock wheels. With every high-speed rotation of a steel rim mounted on rubber, the metal gradually weakens.
If the rim was on a solid hub, like this pencil lying on the desk, and we apply a load to the outside of the rim, then the rim can't deflect and is supported by the solid hub. If, however, it's supported on rubber pads, now we deflect the rim and tensile stresses develop on the underside of the rim of the wheel. Eventually, the stresses were sufficient to cause a fatigue crack. So the crack grows by a tiny amount with each repetition of the load until eventually it is so big that the pencil breaks. During the service of the wheel, very careful examinations are made using very sophisticated apparatus, but it's always focused on looking for cracks initiating in the contact area between the outside of the rim and the steel rail. In a solid wheel, that is where we'd expect fatigue cracks to grow. But because of this flexible rim and the bending stresses being a maximum on the underside of the rim, this is out of sight and out of mind and not being looked at by the inspection process.
During its lifetime, the resilient wheel on ICE 884 had travelled over 1.8 million kilometres. But tragically for the passengers on June the 3rd, 1998, this was its last journey. A severe stress fracture in the steel rim caused it to rupture and detach from its steel core. The rubber pads disintegrated, and the broken rim jammed up into the carriage.
That was the part of metal that had gone through the floor of the carriage, alerting the passenger to the danger.
The train was able to continue in this unstable condition for another 5 kilometres, but when it approached a set of track points with a guide rail, disaster was certain. The other end of the broken wheel rim caught on the guide rail, ripping it up and out of place, derailing all the carriages behind.
The train was then being pulled by 2 different forces. It was trying to go straight on, but the wheels were pulling it sideways.
The first 3 cars decoupled and continued under the bridge. But the remaining carriages now had nowhere else to go but straight into it. The collision was so extreme that the bridge completely collapsed on top of the train. So a combination of a broken wheel rim and the proximity of the guide rail to a 300-ton concrete bridge resulted in the largest death toll in high-speed rail history. After the crash, many changes were made by the German Federal Department of Railways. The Eschede disaster showed that if a train is partially derailed, it's most likely to suffer complete derailment when it reaches a set of track points. So it was decided that all track points should be moved away from bridges and other potentially hazardous structures. Additionally, with its high-speed design flaw now starkly exposed, the resilient wheel had had its day.
After the accident, these resilient wheels were withdrawn from service, and I think it's highly unlikely that they will ever be used again for high-speed train applications.
The rail industry always learns from rail accidents, and one of the lessons from this one was that the resilient wheels used on these ICE trains were unsuitable at the high speeds that the trains go. They were fine on trams, but not on the ICEs.
The resilient wheel was replaced by the more trustworthy solid monoblock wheel. But although the broken wheel was the root cause of the accident, there was a major additional factor that made the outcome far worse than it might have been. The twisted wreckage of ICE 884 was chilling proof that the train's structural integrity had been seriously inadequate.
One of the things that made it worse was the way that the carriages jackknife, piling into each other and crushing the people inside.
The ICE carriages were made of a lightweight aluminium body shell welded to a heavy steel underframe. As the carriages concertinaed into themselves on impact with the bridge, many split along the weld lines as if by a tin opener, crushing passengers inside or spitting them out onto the track. It was clear that the train just hadn't been designed to withstand a high-speed collision. According to Dr. Kuhlwetter, a retired lawyer for the Federal Department of Railways, design practices have now changed.
Heute wird ein Fahrzeug konstruiert, nicht nur bei der Eisenbahn, sondern auch beim Auto, auch beim Flugzeug, mit äußerster Ausnutzung der Materialtragfähigkeit. Man konstruiert mit Grenzwerten, man konstruiert mit dem Computer. Früher hat man Fahrzeuge gebaut mit, ich sag mal, dem dicken Daumen.
Like the ICE train, the AGV has welded aluminium body shells for their weight advantage. But the difference is, before they were even built, the AGV carriages were tested to their limits using advanced computer modelling.
Et donc nous avons besoin d'une caisse très rigide. Et pour cela, on emploie les outils normaux de l'ingénieur, à savoir du calcul de structure, de la modélisation par, comme on appelle, par élément fini, de manière à pouvoir modéliser l'ensemble de la structure et ensuite l'ensemble de la réponse de la structure.
The AGV's engineers would rather not wait until a crash to know how their carriages will respond. So calculations are made based on the property limits of the materials used and the potential forces exerted in a collision. With this information, engineers strive to perfect their design for maximum safety. But the key to the AGV's crashworthiness isn't just in the individual strength of its carriages, but in the rigidity of the train as a whole. This is achieved by addressing the very same problem that Deutsche Bahn were trying to solve with the resilient wheel on the ICE, vibration.
Nous faisons des calculs prenant en compte les deux situations, le vibratoire et la sécurité en cas de crash, de manière à avoir la structure qui réponde aux deux considérations.
On all trains, the wheels are housed in a chassis known as a bogie. On conventional trains, including the German ICE fleet, these bogies are located at the front and back of each carriage, directly below the passengers. Reducing vibration here depends heavily on good suspension. But the AGV has what are known as articulated bogies, which are located under the vestibules between carriages. Moving the bogies away from the passengers eliminates the majority of vibration and rolling noise on board. But the bonus of the articulated bogie is that not only does it solve the issue of passenger comfort, its very positioning contributes to the rigidity of the train as a whole in the event of a derailment.
Et vous avez les deux voitures, une là, qui sont très solidement connectées par une articulation, et c'est ce qui fait la clé à la fois des qualités aérodynamiques et de confort, mais aussi de sécurité du train. C'est pratiquement indissociable.
The couplings on the ICE train were not very different from this old train, where the bogies are separate on each carriage, and that means there's the real potential in an accident to jackknife like this. Whereas if you have modern articulated bogies, the train is held rigid and can't jackknife in that way.
When carriages are mounted on conventional bogies, like ICE 884, in the event of a derailment, there's potential for significant pivotal movement between them. If one car derails in a certain direction, the momentum can cause the next one to jackknife the opposite way, as was the case in Eschede. But the positioning of the articulated bogies on the AGV means the carriages are strongly supported at the point of pivotal movement, making for a far more rigid train. So if one car derails and moves in a certain direction, the one behind is pulled the same way. Articulated bogies were already in use on the AGV's predecessor, the TGV, at the time of the Eschede disaster, and proved their worth dramatically 5 years earlier.
Nous avons eu un effondrement de terrain localisé sous la voie et le train à grande vitesse est passé à 300 à l'heure au-dessus de cette zone où la voie n'était plus du tout tenue. C'était une voie complètement non stabilisée. La motrice, le premier véhicule de la motrice est passé, tout le reste du train a déraillé Et ça s'est très très bien comporté. Le train ne s'est pas couché, le train, grâce à notre système articulé, le train ne s'est pas désassemblé. Il n'y a eu pratiquement aucun blessé.
But the AGV has a remarkable innovation over the TGV. Like most trains, the TGV is driven by locomotive engine cars at either end of the train set, which move the inert carriages in between. But the AGV has no need for engine cars, because its carriages can move themselves.
C'est tout à fait nouveau. La motorisation de la GV se fait, comme on l'a dit, avec une motorisation répartie, ce qui signifie que nous avons installé les moteurs de traction directement à l'intérieur du bogie. Ici, vous avez le moteur, c'est un moteur de nouvelle technologie, un moteur à aimant permanent. Le gros avantage, c'est que c'est un moteur très puissant, petit et léger.
Never before has a high-speed train motor been powerful enough and small enough to fit directly inside an articulated bogie. Distributing these powerful lightweight motors across the train in this way is what makes the AGV capable of its blistering speed. In fact, the AGV's revolutionary bogies were used to set the new world train speed record in April 2007. Lacote created a super-fast hybrid train by sandwiching two of his trailblazing bogies between two TGV locomotives.
Il faut dire que lorsque l'on a dépassé la vitesse du précédent record, qui était 515 à l'heure, nous étions très heureux. Nous voulions repousser les limites. Ce sont des limites qui sont liées à la voie, qui sont liées à la dynamique du train, qui sont liées à l'aérodynamique, qui sont liées au captage du train avec la vitesse critique de la caténaire. On ne pouvait pas dire qu'on était certain. On avait une expérience, on avait des modélisations, nous avions fait des calculs, nous étions confiants, mais pas certains.
But not only is this new power bogie good for speed, there's a big advantage for the stability of the train set too.
Le fait que les moteurs soient très bas, ça va dans le bon sens vis-à-vis de l'abaissement du centre de gravité. Donc tout ceci concourt à avoir un train très stable.
Positioning the weight of the engine as low as possible in the train makes it far more likely to remain upright in a derailment. But for all this groundbreaking engineering, rail safety has always relied and will always rely on one simple principle: being able to stop. On June the 27th, 1988, commuters were making their way home from the underground platforms at the Gare de Lyon, one of Paris's busiest stations. Among the crowds was Dominique Pavie.
Je rentrais chez moi, Villeneuve-Saint-Georges, donc du musée du Louvre à Villeneuve-Saint-Georges, je passais par la gare de Lyon. Il était assez tard. Arrivé à la gare, je trouve un omnibus qui allait partir. Je monte dedans, dans la deuxième voiture. Cet omnibus ne part pas. On nous annonce qu'il y avait des pannes, des retards, etc. Il faisait chaud. Il était bondé, il était plein de gens. Et puis j'attendais, comme tout le monde, assise.
But as Dominique waited for her delayed train to depart, she saw a quicker way to get home.
Puis je vois arriver sur le quai d'en face un direct pour Villeneuve-Saint-Georges où j'habitais. Donc j'ai décidé de quitter l'omnibus qui ne partait pas. Enfin, je suis arrivée à descendre. J'ai fait 5 pas en direction de la tête du train. 5 pas sur le quai. Et au 5e pas, il s'est passé quelque chose que je n'ai pas tout de suite compris. Ce que j'ai perçu en premier, c'est un bruit sourd et métallique. Une fumée noire, une poussière noire.
In her split-second decision to leave her delayed train, Dominique Pavie avoided a catastrophic collision. The train she had just left was hit with colossal force by a runaway train, completely crushing the carriage that she'd been in just moments before.
Lorsque la poussière retombait, ce qui m'a le plus frappé, c'est ce qu'on appelle le silence de mort. Et ce qui est extrêmement douloureux, c'est qu'après sont arrivés les gémissements, des gémissements vagues, tout doucement, des pauvres malheureux qui étaient écrasés. J'ai perçu évidemment des choses pour lesquelles je n'ai pas de mots.
The impact was so severe that the front carriages embedded in each other, making it difficult for rescuers to tell which train was which. 59 people were killed in the disaster, and many others were seriously injured. So what had caused this extraordinary collision? Why had a runaway train come into an occupied platform? And crucially, why had it not been able to stop?
One of the most feared events in the rail industry is a runaway train, and this was one. But the question was, why had the brakes failed?
The person charged with finding the answers was seasoned disaster investigator Jean-Pierre Pascal.
Ce qui est certain, c'est que le train qui a tamponné est descendu dans la gare souterraine qui est en profondeur avec une pente très forte de descente sans ses freins mécaniques.
Upon inspecting the wreckage of the runaway train, Pascal noticed something very unusual with the mechanical air brakes.
Le robinet qui contrôle toute la conduite d'air comprimé du train, qui se trouve juste derrière la motrice de ce train, était fermé. Il aurait dû être ouvert, ce robinet. Normalement, lorsque la conduite est coupée de cette façon-là, le système pneumatique est fait de telle façon que tous les freins de toutes les voitures qui sont derrière se bloquent automatiquement et le train ne peut pas partir.
But why was the valve closed? And if the brakes were locked on, how was the train able to move? A few days after the accident, a passenger came forward and admitted pulling the emergency cord, which automatically applied the brakes, because she'd forgotten to get off the train as it was pulling away from her stop, 10 kilometres before the Gare de Lyon. The investigation quickly shifted focus to the delay that this had caused at the suburban station. Resetting the brakes after an emergency application should have been a simple procedure for the driver, but it was discovered that in doing so, he had inadvertently closed the air brake valve, locking the brakes on. In his desperation to unlock the brakes, the driver then made a critical error.
Comme il ne pouvait pas partir, il a, on appelle ça, purgé le système, c'est-à-dire que, parce qu'il y a un réservoir d'air qui reste gonflé, même si la conduite est coupée, et qui serre les freins. Et si on veut desserrer les freins, on peut ouvrir une petite trappe, une petite fuite sur ce réservoir et le vider. C'est ce qu'il a fait.
In order to fully unlock his brakes, the driver systematically bled the air from the air brake reservoir of each and every carriage on the train. It worked, and he was finally able to drive away. But the driver had no idea that with the air valve still closed, he was speeding towards Gare de Lyon with brakes that were unable to replenish.
À 3 km, on s'aperçoit, il essaye de ralentir, le conducteur, il s'aperçoit que les freins ne marchent pas. Il prévient par radio le centre de contrôle de la gare de Lyon il sait où il va, il sait qu'il va descendre, qu'il va aborder une descente très forte et que son train ne s'arrêtera pas.
An accident was now unavoidable, but at this stage, a collision wasn't.
There had still been one last chance to avoid a collision with another train. The control system in the Gare de Lyon area has a safety feature to ensure that no train can be directed into an already occupied platform. But unfortunately, investigators discovered that once the control centre heard about the runaway train, they locked down the whole system.
In order to keep all other trains out of harm's way, the control centre initiated what's called a general closure procedure, which gave them complete manual control over the usually automated routing system. They now had the ability to switch every signal to red, freezing all other train traffic into the Gare de Lyon. But in overriding the automated system, they'd made a disastrous error of their own. They had disabled the one automatic safety feature that would have directed the runaway train into an empty platform. Disaster was now inevitable. The speeding train ploughed into the waiting train, crushing the front two carriages. Dominique Pavie can't quite believe she survived.
J'ai eu vraiment la sensation d'avoir évité la mort à 5 secondes. Et une mort horrible parce que j'étais au début du deuxième wagon, donc j'aurais été complètement écrasée en accordéon, quoi. Ça c'est sûr, c'est sûr. Donc vraiment, pour moi, j'ai frôlé la mort de très très près, quoi.
Ce sont des choses, c'est catastrophique, mais comment dire ça n'arrivera jamais? On ne peut pas le dire. On ne peut pas dire que ça n'arrivera jamais. Ce qu'on peut dire, c'est que tout est fait pour que ça n'arrive pas.
After the Gare de Lyon incident, many changes were made to rail systems across Europe. Air brake valves were removed from engine cars, and passenger-activated emergency brakes were replaced with emergency driver intercoms to ensure that only the driver is able to stop the train. Changes were also made to the general closure procedure at French main stations, so that staff could manually operate the signalling system without overriding pre-programmed automatic routing features. But the top priority for engineers was to eliminate the risk of brake failure altogether. Among the technological safeguards in the AGV is a braking system in which it is not possible to bleed air from the main brakes. For one good reason: there is no air. Instead, the very thing that powers the train is also what breaks it.
Ce moteur à aimant permanent fonctionne en général comme moteur, mais il peut fonctionner en générateur comme une dynamo. C'est-à-dire qu'avec l'inertie du train, la dynamo oppose de la résistance au mouvement et cela freine le train et en même temps cela crée de l'électricité. Donc un seul objet et deux fonctions, soit traction, soit freinage.
Using a motor in this way is known as dynamic braking. By simply reversing the magnetic field of a motor, huge resistance is imposed on a train's forward momentum, slowing it down and generating kinetic energy. This energy is normally wasted as heat through overhead resistors. But the AGV has a remarkable alternative use for it. These brakes are regenerative, which means the braking energy created is not wasted as heat, but returned from the train to the national grid as electricity. In fact, up to 20% of the AGV's electrical consumption can be recovered with regenerative braking, energy efficiency that Le Côte is extremely proud of.
Donc on produit de l'électricité, on renvoie l'électricité à travers la caténaire au réseau public, et avec ça on peut vendre notre électricité, on peut faire un peu d'argent en freinant ce train.
The AGV's regenerative brakes improve safety as well as profits. As this is an electric, not a compressed air system, the AGV simply cannot be bled of its braking power, as was the runaway train at the Gare de Lyon. No matter how effective a train's brake system, the possibility of a head-on collision can never be completely eliminated. Somehow, passengers have to be protected from the violent forces of a potential impact. Engineer Thierry Yonnet has devoted a career to this challenge, and he's now helped to devise a revolutionary crash shock absorber that's built into the nose of the AGV.
Donc c'est un système anti-collision. En cas de collision, on va absorber successivement par 3 modules une partie de l'énergie.
A huge volume of energy is generated by a high-speed impact, and it's the task of an anti-collision system to absorb as much of it as possible. Yonnet's system does this in 3 phases.
Dont le premier est essentiellement un système d'usinage mécanique. Si on s'en approche, on peut voir qu'on a tout un système de fixation de ce coupleur sur une plaque. Et cette plaque, elle, est maintenue par 4 vis qui servent de fusibles mécaniques. En cas de choc violent, ces vis vont casser, elles sont là pour ça, elles vont céder. Et l'ensemble, tout l'ensemble, va se propulser à l'intérieur.
After these fuses have broken, a second absorption system consisting of a large steel buffer absorbs additional energy. And behind that is a third system of pre-folded steel plates designed to crumple. The total energy absorbed helps maintain the structural integrity of the train. But if train journeys are to be made completely safe, advances in train design have to be matched by technology on the line. It was a quiet morning on October the 24th, 1979, in the small Scottish town of Invergowrie, on the banks of the Tay estuary. Katrina Wright and her mother were on a train bound for Dundee.
We were going through to Dundee, me and my mum. We were sitting second carriage from the back, and we were just going Christmas shopping early. It came to a halt just after Invergowrie station. It wasn't due to stop there, so we wondered why it had stopped. And then the guards told us that it had broken down.
But what Katrina and her mother didn't know was that a Glasgow to Aberdeen express train was heading straight for them at 70 miles per hour. The guard on the speeding express train, George McRitchie, was riding in the brakes van.
Coming around the bend when I seen it on the little train in the line, I didn't think it was on our line. I thought it was on the coming towards us, but here it was on our line. Next thing, I went to put the brake on.
But as McRitchie scrambled for the emergency brake in his van, it was too late.
The express had a quarter of a mile to stop, but it didn't, and collided with the rear of the first train with such force that both reared up in a tangle of tearing metal.
The tables and everything got turned, and we got thrown about all over the place, and then it came to a halt.
The impact of the collision was so severe that it catapulted the back four carriages of the stationary train over the sea wall and into the estuary.
There was complete silence, and then everybody started screaming and crying. It would have been much worse if the tide had been in. So I don't think we would have made it, to be honest.
Had Katrina's train plunged into water, she and the others in her carriage would almost certainly have drowned. But as it was, the soft mud in the bay cushioned the impact. Up on the track in his now derailed brake van was George McRitchie.
Banged my head and sort of stunned. You know, when I come to, I said, oh, jeez. I looked outside, I said, oh, jeez.
The two-man driving crew of the express died on impact. The senior driver had been a close friend of McRitchie's.
That's when I seen my driver and second man lying there. And I took a ball and covered the bodies up. And boom, had a hole right in the middle, as if he'd been shot, where he'd hit his head when they applied the brake.
3 more died in the rear carriage of Katrina Wright's train, taking the death toll to 5.
It does give me a lump in my throat, because you think of the loss of life and just people doing their normal job and unfortunately not going home at the end of the day. It's quite tragic, yeah. And to think we actually came out of that alive.
So what was it that had brought such tragedy to the quiet town of Invergowrie?
Once again, the inquiry team will begin their investigations, this time concentrating on the signalling system here, which may have led these 2 trains to disaster.
The investigation started 2 miles back at the signal box in Long Forgan. The type of signals in operation here were of the old semaphore variety, common on railways all over the world at this time. If the signal's arm is raised to an angle of 45 degrees, the driver may proceed. If the arm is horizontal, the signal is at danger, instructing the driver to stop. Long Forgan had a typical setup, consisting of an initial distance signal to warn the driver to slow the train, a signal box for operating the signals, and a second signal further down the line to bring the train to a complete stop. On the day of the crash, John McRae of the Tayside Fire Brigade came to investigate the signals at Long Forgan.
And we discovered there was a signal down there, just beside that tree, roughly in that area. So we know there was a signal there, and the signal was showing an incorrect signal, inasmuch that rather than being horizontal for stop or 45 for go, it was halfway between.
McRae discovered that although the signalman had set the lever in his box to danger to halt the express, the semaphore arm did not in fact return to the full horizontal stop position. The driver interpreted the ambiguous signal as go and accelerated on towards Invergowrie, unaware of the stationary train on the line ahead. Disaster was now imminent. As the express train came round the bend at 70 miles per hour, it couldn't possibly stop in time, colliding with the stationary train and smashing its back 4 carriages into the bay. But why had the driver continued through an ambiguous signal? In the official report into the crash, it was suggested that a driver's changing angle of vision to an ambiguous signal could possibly affect his reading of it. Railway signalling expert Roy Bell is setting out to recreate what the driver may have seen.
We're approaching a signal now which is imperfectly shown. A driver would normally not take this as proceed. However, as we get closer to the signal, the angle as we're viewing it changes, and it is possible, just possible, that a driver might take the signal as proceed. And that's what, in my opinion, happened at Invergary.
The driver had clearly been let down by an archaic mechanical system, but engineers needed to know exactly how it had failed him.
Traditional semaphore signals have been used on railways for well over 100 years, and they're simply operated by a lever being pulled.
When a signal lever is pulled, a system of cogs and chains at the signal box controls a wire that runs to the signal post, adjusting the angle of the arm. So why was the signal arm at Longforgan at such a strange angle?
Could have been in the position it was because it had been a cold night and the tension on the wire had increased as the temperature got colder, which meant that it wasn't so easy for the signal to return to the full horizontal stop position.
When questioned, several signal men who worked at Longforgan admitted having problems with the same signal during periods of cold weather. If one cold night could cripple the mechanics of the semaphore system and cause such devastation, it was time to re-examine signalling technology. Immediately after the accident, the Longforgan signal box and many others across the country were fitted with repeaters, which indicated the exact position of the semaphore arm to the signalman, so that he'd know if it had malfunctioned. But the mechanical flaws of the semaphore system had been exposed, and gradually these signals were phased out in favour of colour lights with less potential for ambiguity and significantly lower maintenance costs. But surprisingly, they haven't stopped signalling disasters. In other accidents, sunlight, shadows and scaffolding have all been cited as factors in obscuring a driver's view. It remains clear that any form of signalling still carries with it the possibility of a driver passing a signal at danger. Engineers in Europe are now developing a radical new idea for signals, getting rid of them altogether. And their system involves such advanced technology that in the future, the high-speed train driver himself may also be a thing of the past.
Already, the technology is there for trains to travel at hundreds of miles per hour without a driver.
A revolutionary train protection system is now being implemented in Europe that will make passengers safer than ever. It's called the European Rail Traffic Management System, ERTMS.
At the moment, trains are controlled by outside signals, which the driver has to see. The crucial point about ERTMS is that signals will be directly transmitted into the train's control system so that they can't possibly be overridden or missed by the driver.
A unique satellite radio communication system transmits signalling instructions from a control centre directly to a computer in the driver's cab, called the European Train Control System, ETCS. The computer uses this information to calculate the safest maximum speed at which the driver can travel. If the driver disobeys the computer, it will automatically slow the train to within the safe limit. The ETCS onboard computer virtually eliminates the possibility of a signalling disaster. But there are other benefits too. A fully equipped ETCS train constantly transmits its location to the control centre, allowing trains to run closer together and line capacity to be increased without safety risks. This groundbreaking technology is already in its infancy in more than 10 different countries and is set to be installed on all European high-speed lines in the future.
Once ETCS is introduced throughout Europe at its highest level, it will be the end of an era for railway signalling because essentially the trains will be controlled from outside rather than from in the cab.
If computers are now in control of high-speed trains, it could be argued that there's no need for a driver. The AGV is equipped with ETCS technology, but François Lacoute is not about to let his driver go.
Donc cette association entre l'automatisme vis-à-vis de tous les événements prévus et de l'homme qui sait réagir face à un imprévu, c'est ça qui maintenant va faire la sécurité absolue du train à grande vitesse. Ça doit rester la solution. Le conducteur reste indispensable à bord.
There are a number of driverless services operating around the world, but they exist as relatively low-speed metro links. As yet, there are no driverless high-speed trains in commercial operation. But some suggest that's not because of the limitations of technology. It's psychological.
People will not accept the idea of a train being driven at several hundred miles an hour along busy tracks with lots of other trains without there being a driver there to reassure them that their journey will be safe.
Whatever the future for the high-speed train driver, there's no doubt that the huge advances in safety technology have made the possibility of disaster increasingly remote. And as European high-speed lines embrace this cutting-edge safety system, François Lacoute is proud to have a train that's ready for the challenge.
Je voulais le train pour le réseau ferroviaire à grande vitesse de l'Europe, c'est-à-dire un train complètement européen, capable de toutes les lignes ferroviaires de l'Europe et un train capable de la vitesse du futur, c'est-à-dire au moins 360 km/h. C'était le train du futur de l'Europe.